Welcome to the I Can't Sleep podcast, where I read random articles from across the web to bore you to sleep with my soothing voice. I'm your host, Benjamin Boster, and today's episode is from a Wikipedia article titled Stalactite. A stalactite, from ancient Greek stalaktos, dripping, from stalacine, to drip, is a mineral formation that hangs from the ceiling of caves, hot springs, or man-made structures such as bridges and mines. Any material that is soluble and that can be deposited as a colloid, or in suspension, or is capable of being melted, may form a stalactite. Stalactites may be composed of lava, minerals, mud, peat, pitch, sand, cinder, and ambrat. A stalactite is not necessarily a speleothem, though speleothems are the most common form of stalactite because of the abundance of limestone caves. The corresponding formation on the floor of the cave is known as a stalagmite. The most common stalactites are speleothems, which occur in limestone caves. They form through deposition of calcium carbonate and other minerals, which is precipitated from mineralized water solutions. Limestone is the chief form of calcium carbonate rock, which is dissolved by water that contains carbon dioxide, forming a calcium bicarbonate solution in caverns. The solution travels through the rock until it reaches an edge, and if this is on the roof of a cave, it will drip down. When the solution comes into contact with air, the chemical reaction that created it is reversed and particles of calcium carbonate are deposited. An average growth rate is 0.13 millimeters a year. The quickest growing stalactites are those formed by a constant supply of slow dripping water, rich in calcium carbonate and carbon dioxide, which can grow at 3 millimeters per year. The drip rate must be slow enough to allow the CO2 to degas from the solution into the cave atmosphere, resulting in deposition of CaCO3 on the stalactite. Too fast a drip rate and the solution, still carrying most of the CaCO3, falls to the cave floor where degassing occurs and CaCO3 is deposited as a stalagmite. All limestone stalactites begin with a single mineral-laden drop of water. When the drop falls, it deposits the thinnest ring of calcite. Each subsequent drop that forms and falls deposits another calcite ring. Eventually, these rings form a very narrow, hollow tube commonly known as a soda straw stalactite. Soda straws can grow quite long, but are very fragile. If they become plugged by debris, water begins flowing over the outside, depositing more calcite and creating the more familiar cone-shaped stalactite. Stalactite formation generally begins over a large area with multiple paths for the mineral-rich water to flow. As minerals are dissolved in one channel slightly more than other competing channels, the dominant channel begins to draw more and more of the available water, which speeds its growth, ultimately resulting in all other channels being choked off. This is one reason why formations tend to have minimum distances from one another. The larger the formation, the greater the interformation distance. The same water drops that fall from the tip of a stalactite deposit more calcite on the floor below, eventually resulting in a rounded or cone-shaped stalagmite. Unlike stalactites, stalagmites never start out as hollow soda straws. Given enough time, these formations can meet and fuse to create a speleothem of calcium carbonate, known as a pillar, column, or stalagnate. Another type of stalactite is formed in lava tubes, while molten and fluid lava is still active inside. The mechanism of formation is the deposition of molten dripping material on the ceilings of caves. However, with lava stalactites, formation happens very quickly in only a matter of hours, days, or weeks, whereas limestone stalactites may take up to thousands of years. A key difference with lava stalactites is that once the lava has ceased flowing, so too will the stalactites cease to grow. This means that if the stalactite were to be broken, it would never grow back. The general term lavasicle has been applied to lava stalactites and stalagmites indiscriminately and evolved from the word icicle. Like limestone stalactites, they can leave lava drips onto the floor that turn into lava stalagmites and may eventually fuse with the corresponding stalactite to form a column. The shark-tooth stalactite is broad and tapering in appearance. It may begin as a small driplet of lava from a semi-solid ceiling, but then grows from accreting layers as successive flows of lava rise and fall in the lava tube, coating and recoating the stalactite with more material. They can vary from a few millimeters to over a meter in length. As lava flows through a tube, material will be splashed up on the ceiling and ooze back down, hardening into a stalactite. This type of formation results in an irregularly shaped stalactite, looking somewhat like stretched taffy. Often they may be a different color than the original lava that formed the cave. When the roof of a lava tube is cooling, a skin forms that traps semi-molten material inside. Trapped gases expansion forces lava to extrude out through small openings that result in hollow tubular stalactites, analogous to the soda straws formed as depositional speleothems in solution caves. The longest known is almost 2 meters in length. These are common in Hawaiian lava tubes and are often associated with a drip stalagmite that forms below as material is carried through a tubular stalactite and piles up on the floor beneath. Sometimes the tubular form collapses near the distal end, most likely when the pressure of escaping gases decreased and still molten portions of the stalactites deflated and cooled. Often these tubular stalactites acquire a twisted vermiform appearance as bits of lava crystallize and force the flow in different directions. These tubular lava helictites may also be influenced by air currents through a tube and point downward. A common stalactite found seasonally or year-round in many caves is the ice stalactite, commonly referred to as icicles, especially on the surface. Water seepage from the surface will penetrate into a cave, and if temperatures are below freezing, the water will form stalactites. They can also be formed by the freezing of water vapor. Similar to lava stalactites, ice stalactites form very quickly within hours or days. Unlike lava stalactites, however, they may grow back as long as water and temperatures are suitable. Ice stalactites can also form under sea ice when saline water is introduced to ocean water. These specific stalactites are referred to as brinicles. Ice stalactites may also form corresponding stalagmites below them, and given time may grow together to form an ice column. Stalactites can also form on concrete and on plumbing where there is a slow leak and where there are calcium, magnesium, or other ions in the water supply, although they form much more rapidly there than in the natural cave environment. These secondary deposits, such as stalactites, stalagmites, flowstone, and others, which are derived from lime, mortar, or other calcareous material in concrete outside of the cave environment, cannot be classified as speleothems due to the definition of the term. The term calthemite is used to encompass these secondary deposits, which mimic the shapes and forms of speleothems outside the cave environment. The way stalactites form on concrete is due to different chemistry than those that form naturally in limestone caves, and is due to the presence of calcium oxide in cement. Concrete is made from aggregate, sand, and cement. When water is added to the mix, the calcium oxide in the cement reacts with the water to form calcium hydroxide, CaOH2. Over time, any rainwater that penetrates cracks in set hard concrete will carry any free calcium hydroxide in solution to the edge of the concrete. Stalactites can form when the solution emerges on the underside of the concrete structure where it is suspended in the air, for example, on a ceiling or a beam. When the solution comes into contact with air on the underside of the concrete structure, another chemical reaction takes place. The solution reacts with carbon dioxide in the air and precipitates calcium carbonate. When this solution drops down, it leaves behind particles of calcium carbonate, and over time these form into a stalactite. They are normally a few centimeters long and with a diameter of approximately 4 to 5 millimeters. The growth rate of stalactites is significantly influenced by supply continuity of Ca2 plus saturated solution and the drip rate. A straw-shaped stalactite, which has formed under a concrete structure, can grow as much as 2 millimeters per day in length when the drip rate is approximately 11 minutes between drops. Changes in leachate solution pH can facilitate additional chemical reactions, which may also influence calthemite stalactite growth rates. Stalactites are first mentioned, though not by name, by the Roman natural historian Pliny in a text which also mentions stalagmites and columns, and refers to their formation by the dripping of water. The term stalactite was coined in the 17th century by the Danish physician Olav Orm, who coined the word from the Greek word stalaktos, dripping, and the Greek suffix ites, connected with or belonging to. A rusticle is a formation of rust similar to an icicle or stalactite in appearance that occurs deep underwater when iron-loving bacteria attack and oxidize wrought iron and steel. They may be familiar with underwater photographs of shipwrecks, such as the RMS Titanic and the German battleship Bismarck. They've also been found in the number 3 turret, 8-inch gun turret on the stern remains in the place of the USS Indianapolis. The word rusticle is a portmanteau of the words rust and icicle, and was coined by Robert Ballard, who first observed them on the wreck of the Titanic in 1986. Rusticles on the Titanic were first investigated in 1996 by Roy Collimore. A previously unknown species of bacteria living inside the Titanic's rusticles was discovered in 2010 by Henrietta Mann. Rusticles can form on any submerged steel object and have been seen on other subsea structures, such as mooring chains and subsea equipment. They form more rapidly in warmer climates and can form in water with little to no dissolved oxygen. The rusticle consists of up to 35% iron compounds, including iron oxides, iron carbonates, and iron hydroxides. Rusticles are found in tube shapes of iron oxides, which are vertical to one another. Rusticles are found to grow at approximately 1 centimeter a year and are most often found in areas of sunken holes underwater. The remainder of the structure is a complex community of symbiotic or mutualistic microbes and fungi that use the rusting metal as a source of food, causing microbial corrosion and collectively producing the mineral compounds that form the rusticle as waste products. Rusticles have been found to most often be composed of iron, calcium, chloride, magnesium, silica, sodium, and sulfate, while there are other chemical compositions of rusticles, but in much smaller quantities. Structurally, rusticles contain channels which allow water to flow through them, and they seem to build up in a ring structure similar to the growth rings of a tree. They are very delicate and can easily disintegrate into fine powder on even the slightest touch. The outer surface of a rusticle is smooth red in appearance from the iron 3 oxide, while the core is bright orange due to the presence of crystals of goethite. There are several morphologies of the rusticle, some of which are conical, cylindrical, and rustical on the seafloor. An icicle is a spike of ice formed when water falling from an object freezes. Icicles can form during bright, sunny, but sub-freezing weather, when ice or snow melted by sunlight or some other heat source, such as a poorly insulated building, refreezes as it drips off under exposed conditions. Over time, continued water runoff will cause the icicle to grow. Another set of conditions is during ice storms, when rain falling in air slightly below freezing slowly accumulates as numerous small icicles hanging from twigs, leaves, wires, etc. Thirdly, icicles can form wherever water seeps out of or drips off vertical surfaces, such as road cuts or cliffs. Under some conditions, these can slowly form the frozen waterfalls favored by ice climbers. Icicles form on surfaces which might have a smooth and straight or irregular shape, which in turn influences the shape of an icicle. Another influence is melting water, which might flow toward the icicle in a straight line or which might flow from several directions. Impurities in the water can lead to ripples on the surface of the icicles. Icicles elongate by the growth of ice as a tube into the pendant drop. The wall of this ice tube is about zero point 0.1 millimeters and the width 5 millimeters. As a result of this growth process, the interior of a growing icicle is liquid water. The growth of an icicle, both in length and in width, can be calculated and is a complicated function of air temperature, wind speed, and the water flux into the icicle. The growth rate in length typically varies with time and can, in ideal conditions, be more than 1 centimeter per minute. Given the right conditions, icicles may also form in caves, in which case they are also known as ice stalactites. They can also form within salty water, brine, sinking from sea ice. These so-called brinicles can kill sea urchins and starfish, which was observed by BBC film crews near Mount Erebus, Antarctica. Icicles can pose personal and structural dangers. Icicles that hang from an object may fall and cause injury and or damage to whoever or whatever is below them. In addition, ice deposits can be heavy. If enough icicles form on an object, such as a wire, beam, or pole, the weight of the ice can severely damage the structural integrity of the object and may cause the object to break. This can also happen with roofs, where failure can damage nearby parked vehicles or the contents and occupants of the structure. Icicles on roofs can also be associated with ice dams, which can cause water damage as the water penetrates below the shingles. Large icicles that form on cliffs near highways have been known to fall and damage motor vehicles. Flowstones are sheet-like deposits of calcite or other carbonate minerals, formed where water flows down the walls or along the floors of a cave. They are typically found in solution caves, in limestone where they are the most common speleothem. However, they may form in any type of cave where water enters that has picked up dissolved minerals. Flowstones are formed via the degassing of vadose percolation waters. Flowstone may also form on man-made structures as a result of calcium hydroxide being leached from concrete, lime, or mortar. These secondary deposits created outside the cave environment, which mimic the shapes and forms of speleothems, are classified as calthamites and are associated with concrete degradation. Flowing films of water that move along floors or down positive sloping walls build up layers of calcium carbonate, calcite, aragonite, gypsum, or other cave minerals. These minerals are dissolved in the water and are deposited when the water loses its dissolved carbon dioxide through the mechanism of agitation, meaning it can no longer hold the minerals in solution. The flowstone forms when thin layers of these deposits build on each other, sometimes developing more rounded shapes as the deposit gets thicker. There are two common forms of flowstones, tufa and travertine. Tufa is usually formed via the precipitation of calcium carbonate and is spongy or porous in nature. Travertine is a calcium carbonate deposit often formed in creeks or rivers. Its nature is laminated, and it includes such structures as stalagmites and stalactites. The deposits may grade into thin sheets called draperies or curtains, where they descend from overhanging portions of the wall. Some draperies are translucent, and some have brown and beige layers that look much like bacon, often termed cave bacon. Though flowstones are among the largest of speleothems, they can still be damaged by a single touch. The oil from human fingers causes the flowing water to avoid the area, which then dries out. Flowstones are also good identifiers of periods of past droughts, since they need some form of water to develop. The lack of that water for long periods of time can leave traces in the rock record via the absence or presence of flowstones and their detailed structure. Flowstones derived from concrete, lime, or mortar can form on man-made structures much more rapidly than in the natural cave environment due to the different chemistry involved. On concrete structures, these secondary deposits are the result of concrete degradation. When calcium ions have been leached from the concrete in solution and redeposited on the structure's surface to form flowstone, stalactites, and stalagmites. Carbon dioxide is absorbed into the hyperalkaline leachate solution as it emerges from the concrete. This facilitates the chemical reactions which deposits calcium carbonate on vertical or sloping surfaces in the form of flowstone. Concrete-derived secondary deposits are classified as calthamites. These calcium carbonate deposits mimic the forms and shapes of speleothems created in caves, e.g., stalagmites, stalactites, flowstone, etc. It is more likely that calthamite flowstone is precipitated from leachate solution as calcite, in preference to the other, less stable polymorphs, aragonite, and vaterite. Other trace elements, such as iron from rusting reinforcing or copper oxide from pipework, may be transported by the leachate and deposited at the same time as the CaCO3. This may cause the calthemites to take on colors of the leached oxides. Cave onyx is any of various kinds of flowstone considered desirable for ornamental architectural purposes. Cave onyx was a common term in certain areas of the United States, particularly the Tennessee, Alabama, Georgia area, and the Ozarks, during the 19th and early 20th centuries, being applied to calcite speleothems that were banded in a way suggestive of true onyx. There are a number of U.S. caves called onyx caves because of the presence in them of such deposits. Speleology is the scientific study of caves and other karst features, as well as their composition, structure, physical properties, history, ecology, and the process by which they form and change over time. The term speleology is also sometimes applied to the recreational activity of exploring caves, but this is more properly known as caving, potholing, British English, or spelunking, United States and Canadian English. Speleology and caving are often connected, as the physical skills required for in situ study are the same. Speleology is a cross-disciplinary field that combines the knowledge of chemistry, biology, geology, physics, meteorology, and cartography to develop portraits of caves as complex, evolving systems. Before modern speleology developed, John Beaumont wrote detailed descriptions of some Mendip caves in the 1680s. The term speleology was coined by Émile Rivière in 1890. Prior to the mid-19th century, the scientific value of caves was considered only in its contribution to other branches of science, and cave studies were considered part of the larger disciplines of geography, geology, or archaeology. Very little cave-specific study was undertaken prior to the work of Edouard Alfred Martel, the father of modern speleology, who, through his extensive and well-publicized cave explorations, introduced in France the concept of speleology as a distinct area of study. In 1895, Martel founded the Society of Speleology, the first organization devoted to cave science in the world. Other early speleologists include Herbert E. Bauch. Karst is a landscape that has limestone underneath which has been eroded. Caves are usually formed through chemical corrosion via a process of dissolution. Corrosion has several ways of doing this. It can be on carbonate rocks through chemical reactions. In gypsum and rock salt, it can happen physically. And in silicate rocks and warm climate, the decomposition of the materials can happen as well. A speleothem is a geological formation by mineral deposits that accumulate over time in natural caves. Speleothems most commonly form in calcareous caves due to carbonate dissolution reactions. They can take a variety of forms depending on their depositional history and environment. Their chemical composition, gradual growth, and preservation in caves makes them useful paleoclimatic proxies. Caves have an absence of stable temperature, high relative humidity, low rates of evaporation, and limited supply of organic material, which help in creating an environment which is highly favorable for the growth of microbes. Microbial assemblages in caves include archaea, bacteria, fungi, and other microeukaryotes. These highly adapted microbial communities represent the living backbone of cave ecosystems and play a key role in shaping structures and sustaining trophic networks. The creation of an accurate detailed map is one of the most common technical activities undertaken within a cave. Cave maps, called surveys, can be used to compare caves to each other by length, depth, and volume, may reveal clues on speleogenesis, provide a spatial reference for further scientific study, and assist visitors with route finding. Speleologists also work with archaeologists in studying underground ruins, tunnels, sewers, and aqueducts.